Achari?
Sir.
No. Can you see the board?
Sir.
Okay, ma'am. Today we are going to discuss noise in PCM system. In last class, just like that, I started. Now, let me continue from the beginning of noise in PCM system. We know PCM system means a pulse code modulation system in which the message is transmitted in the form of coded pulses. Okay? When PCM signal is transmitting through the channel, the signal will be affected by the channel noise. Okay. As a result of this, what will happen at the output of receiver, PCM receiver, the bits or symbols are decoded wrongly. That means ones are decoded as zeros, zeros are decoded as ones. So this is because of the presence of channel noise. Okay. So in PCM system, there is a one noise component, that is channel noise. Okay. The second one, there is one more noise component which accompanies with the channel noise is quantization noise. What it means, quantization noise? We know in PCM system we are transmitting the signal in the form of coded pulses. How we are getting that code? We are converting analog signal into digital through the process of analog to digital conversion, in which we are using quantization process. So as a result of quantization process, some quantization error is added to the signal. Okay, that itself is treated as a quantization noise. Okay, so there is one more noise component which accompanies with the PCM system or PCM signal is quantization noise. Okay, that means due to the quantization error, whatever you get a noise, that is called quantization noise. Okay, and similarly, due to the presence of noise in the channel, whatever the errors you are getting at the time of decoding the signal, received signal in the receiver, we call it as channel noise. So like that, we will be having two components of noise. One is quantization noise, another is channel noise. So this is very clear. Okay. So at the output of PCM receiver, output noise may be represented as the sum of quantization noise plus, that is the sum of quantization noise and channel noise. Okay, so there are two noise components which are affecting the PCM signal. Okay, and this quantization noise is due to the quantization errors which are resulting due to the quantization process at the transmitter. Okay, that is at the time of modulation. So we can write it as quantization error component, and the same way channel noise is due to the presence of noise in the channel. Okay, and this noise channel noise is affecting the signal in such a way that the signal is decoded wrongly at the receiver. Okay, end of the receiver. So we can think of this noise is due to the channel errors. So we can write it as channel error. Okay, so there are two components. One is quantization error component, and other is channel error component. These two are contributing to the PCM output noise. Okay, so then output noise power can be obtained from these two components by taking their individual mean square values. Okay, the power is always additive. So the total power of output noise is simply the power contributed by the quantization error and the power contributed by the channel error. So you can write this as EQ of T mean square plus EC of T mean square. Okay, so this is about the noise component at the output of a PCM receiver. Okay, now let us talk about the signal. Sorry, someone is disturbing. Okay, now we talk about signal. What about the signal? Signal or the output of receiver is assumed to be the same as that is transmitted. Okay, so S of T. Okay. So therefore, output noise, output signal power. Someone Vaishnavi. Vaishnavi raised her hand. Let me see. Vaishnavi, where are you? You raised your hand. Not coming. Just unmute yourself and you can talk to me. No, if anybody wants to talk to me, you can unmute yourself. I have given that option. Okay, who's on the line? Vaishnavi? Okay. If you really want to talk to me, you can unmute yourself and you can talk to me.
Sir, sorry, sir. It is I wish.
Oh, okay, ma'am. Okay. Nothing now. Nothing now. I'll carry on. Okay, ma'am. So, sorry. Now, the signal power, output signal power S0, P S0 is equal to the signal mean square value. Okay. Once you know these two components, noise component and output signal component, you can determine output SNR as the ratio of signal power, output signal power to output noise power, which is simply equal to S0 by quantization noise power plus channel noise power. Okay, and the output signal power is represented as mean square value of the signal divided by quantization noise is represented as quantization mean square error, and channel noise is represented as channel error mean square value. Okay, channel error mean square value. Okay, so this is what we need to find out to evaluate. In order to evaluate this one, we need to find out the mean square values of the signal and quantization error and the channel error. Okay, now let us do one by one. Okay, we start with the quantization. So we'll see quantization. Noise power. Okay, in quantization process, the result is nothing but quantization error. So which is equal to, the quantization error is equal to the original signal S of T and its quantized form SQ of T. Okay, if the signal S of T is quantized into m number of levels, m levels with quantization interval ui equal to delta. Okay, we are assuming that S of t is quantized into m number of levels with quantization interval delta. Okay, then what about quantization error? The quantization error eq of t, okay, will vary from or between minus delta by 2 to plus delta by 2 within each and every quantization interval. Okay, because there are m number of quantization intervals. Within each and every quantization interval, the quantization error will change from minus delta by 2 to plus delta by 2 with the probability density function. I'm calling this as sum because it is changing from one quantization interval to other quantization level interval. I'm calling it as some ith interval. For any ith interval, it is simply okay, isn't it? Now, let us evaluate mean square value of the quantization error. Okay, how do you find out this? This is equal to sum of quantization mean square values of quantization errors from each and every quantization interval, because there are m number of quantization intervals. So from each and every quantization interval, this quantization error is taken and its mean square values to be evaluated, and then summing up all those. So I can write this mathematically as sum of I equal to 1 to m Madhuri, unmute yourself. Unmute yourself. Ari, mute yourself. So when you enter into the class, be attentive. Why you are diverting yourself. Okay. So here, the summation is carried over m number of quantization intervals. So it varies from I equal to 1 to m. Okay. And integration minus del by 2 to plus del by 2 quantization error square. For simplicity, I'm dropping this argument to t. Okay. I of EQ. So FIQ means a probability density function of quantization error in ith quantization interval. Okay. Into DEQ. Okay, DEQ, isn't it? Now, and this is a symmetric, so I can write it as 2 into summation I equal to 1 to m integral 0 to del by 2 EQ square Fi of EQ into DEQ. Okay. Now, two times, and what about this EQ square summation I equal to 1 to m, and after integrating this and substituting, what do you get? EQ is cubed by 3, 0 to del by 2 into Fi of EQ. Okay, and this is equal to, after substituting everything, it is 2 by 3, and it is del cubed by 8 into, sorry, summation, I missed the summation, 2 by 3 summation by 8 I of EQ. Okay, and we can write this as 2 and 2 to cancel, then it becomes del cubed by 12 and summation I equal to 1 to m, and this is Fi of EQ, that is a probability density function of ith quantization interval, isn't it? And here I can rewrite this equation as del square by 12 summation I equal to 1 to m del into Fi of EQ. Okay, so what do you mean this? It is simply del square by 12, and it is simply equal to del into F1 of EQ plus del into F2 of EQ and so on up to del into Fm of EQ, isn't it? So what does this mean? Del square by 12, and this is equal to del is quantization interval. When you multiply quantization interval with its probability density function, you will get the probability contributed by this quantization interval. So I'm calling it as P1, and the next one is P2, and so on. Finally, Pm. Okay. So you see, sum of all the probabilities. Sum of all the probabilities, that is total probability equal to 1. So it is equal to del square by 12. So this is a, what is this? Quantization error mean square value. Okay. This point I have to remember. Okay. Now let us evaluate signal power. That is output signal power. Output signal power. So how do you find this output signal power? From its mean square value. So yes, mean square. So how do you find this mean square? You can find out its mean square by knowing its probability density function and the variation, isn't it? So what is this actually S of t? S of t is the signal that is to be transmitted, and a receiver the output of a receiver. And when it is, I mean, before transmission, it is quantized, you know. When it is quantized, how it is quantized? It is quantized, S of t is quantized into m levels with the quantization interval, equal to delta. We know this. Okay. When it is quantized in that way, its signal value will change from, or it will change over an amplitude range of So amplitude, or simply amplitude range of S of t equal to what? There are m number of levels. Each level is delta. So the product of these two is equal to the total amplitude range. So S of t is changing over an amplitude range of m into delta, m delta. Okay, or delta m, isn't it? Now what about the amplitude? This is peak to peak value. Okay, so amplitude range means it is nothing but S of t peak to peak value, isn't it? Then what about amplitude of S of t of this? That is plus or minus m delta by 2, isn't it? This means S of t is changing, okay, from minus m delta by 2 to plus m delta by 2 with some probability density function fs of s, some value. Some value here we are treating this as some constant. Some constant. Okay. I'm calling this as a constant. Okay. That means we are assuming S of t is equiprobable. Okay. Equiprobable. When it is equiprobable, we can easily find out its value. How to find its value? Let us say this is the axis of signal and this is the axis of, it's a probability density function fs of s. Okay. And s value is changing from minus m delta by 2 to plus m delta by 2 with constant value. So constant value means this. Let us say this constant value is k. Okay. So the probability density function is equiprobable, means constant, flat, over an interval from minus delta by 2 to plus delta by 2. Now its value can be easily found. How we can find? If we take the area under this probability density function, the area under the probability density function is equal to the probability. Okay. So, and that probability should be equal to 1. Okay. So keeping that in mind, you know, the area, that is k into height into the width of this function, that is m delta, which is equal to the probability, okay, total probability, should be equal to how much? Because the signal is changing from this one end to this another end of the total value. So if you are taking the area under this one, that should be a total probability. So the total probability, you know, for any random process or random signal is 1. So from this, the value of the probability density function k, okay, height equal to 1 by m delta. Okay, keep this in mind. Let us come back to the signal case. So what we need to find out? We need to find out signal power. Okay, so signal power equal to mean square value, and it is equal to, how do you find mean square value? Integral one end of signal variation to another end of a signal variation, m delta by 2. And what is the signal variable? Yes, s of t, but I'm taking it as simply yes, dropping the argument t. So s square into f s of s into ds. Okay, and we know this is a symmetrical. Okay, so that's why I'm writing it as 0, 2 into 0, 2 into integral from 0 to m delta by 2 into s square into fs. What is fs? We know fs. Fs is already fs of s. The probability density function of the signal is equal to 1 by m delta into ds. Okay. Now, if you evaluate, what do you get? 2 by m delta, and after integration, substitution, what happens? S cubed by 3 and 0 to m delta. Sorry, m delta by 2, and it is equal to how much? 2 by m delta, and it is m cubed delta cube by much, ma'am? 8. 8 into 3 means 24. Okay. And how much is this value now? It is equal to 12. So m square, m and m will get cancelled, and the delta will get cancelled, giving us m square divided by, this is a signal power. Okay. Now, before to go any further, let us calculate. Let us determine here itself signal to noise ratio, signal to quantized noise ratio. That is, because it is the most important one. So it is a signal to quantization noise ratio as signal power to quantization noise. Signal power, signal power is just now we calculated m square del square by 12 divided by noise power is simply del square by 12. So these two, when these two get cancelled, giving us m square. Okay, what is m? M is the number of levels into which, okay, I mean message signal is quantized, and after that each and every m level, each and every level of m number of levels is encoded into a sequence of bits. Okay, so if n is the number of bits, it can be written as 2 power n whole power 2, which is equal to 2 power n. Okay, so this is an important relation. Okay. Now let us evaluate